Hello everyone, my name is Victor Barbosa Moraes, and today I'm gonna be talking about the effects of selection bias on online adversarial aware SVM when facing an invasion attack. The outline of the presentation is the motivation of the research, problem statement and objectives, some background, some selection bias in SVM, a little bit of adversarial aware machine learning, a little bit of adversarial sampling, overview of the methodology, a little bit about the data sets used, a little bit of the attacker model that's been considered, how the adversarial sampling technique that's used works, how the adversarial aware online SVM works, the metrics and assumptions, the results and discussion and conclusions. Adversarial machine learning is a machine learning that attempts to fool another machine learning with deceptive inputs. The motivation of this research is to explore the role of adversarial machine learning techniques employed in defending against the spread of phishing attacks. And an important thing about the adversarial machine learning is that usually people fail to consider the context of which it happens. Countermeasures for phishing in social engineering deals with a constantly changing data stream that causes the classifier to malfunction. This is especially problematic in the academic setting because there are not many datasets publicly available. Even when you create your own dataset, it is impossible to capture the dynamic changes in data. To compensate for this, we decided to use an adversarial sampling technique to simulate the attacker. In the attack simulation, one must be careful not to introduce bias. An attacker with the same goal, knowledge, and influence as the simulation should be able to make a successful attack. We also need to try to compensate the misclassification in the classifier. For this, we implemented a modified version of the adversarial aware online SVM. It can change the sample scores during the training and takes into account the adversarial nature of the data. Our objectives are to compare the classifier's performances, that is, between online SVM and adversarial aware online SVM, see the effects of generated labels and on bias metrics, see how changing scores impact bias and performance metrics, and see the effects of selection bias impact on support vectors. The challenge of detecting adversarial attacks using phishing is that the strategies used by the fisher's adaptive time and targeted user. Now for a little bit of the background on previous works, Shirazi et al. Tried to determine the most important features that would distinguish a phishing website from a legitimate one. They tried to avoid anything that was convoluted like DNS routing or that could be compromised later. An example of focus on a feature that was compromised is the work of Verma and Dyer. They based their work on the URL and the reason that the phishing websites with URLs can be identified by a trained person with a certain ease. And now we have URL shortening devices that are widely available that can compromise this study. We believe that the choice of which instances will be kept away from the training can bias how the model behaves. Take this figure as an example of a good selection of instances to be kept away. If we had to select 4 instances to keep away from training, the ones that have been circled are good candidates. They are good candidates because 2 of them can represent the class, and 2 of them represent the ones that most likely will cause some trouble for the classifiers, as represented by the hyperplaning in red. For our adversarial sampling technique, we use the same algorithm as the adversarial sampling attacks against phishing detection by Shirazi et al. And the idea is the same as in the picture. We have a simple input of data, we modify it slightly to cause misclassification. The adversarial-aware machine learning keeps track of the previous samples and then train if sample is likely from malicious agents. We had three research questions. First, if support vectors are used as adversarial sampling technique seed samples, will it cause more misclassification? Second, is there a class imbalance in the generated data by the adversarial sampling technique, and does it negatively affect the classification algorithm? And third, how does the adversarial aware online SVM behave in the worst case scenario with changing scores? This is an overview of the proposed methodology. From the dataset, we selected and reserved 200 samples. The rest of the dataset was used to train and test using five-fold cross-validation. And from the reserved samples, we used the adversarial sampling technique to expand and test the classifier. And then from the test and from the training, we got the scoring measures. We used 5 publicly available datasets. They varied sizes, class proportion, and data type. URL-based features are discrete numbers, binary features can only have 2 values, and trinary features can only have 3 values. We're defining our attacker with a goal of avoiding detection from one machine learning classifier, that is the online SVM or the adversarial-aware online SVM. And it tries to fool it with a set of samples. It knows all phishing websites, features, and outputs, and does the attack after the model has been trained. To illustrate how the adversarial sampling technique works, we created an example of a dataset that is made of instances of 4 features, each of binary values. For a given sample and a list of selected features, the second and third one, the algorithm generates more instances from the unique values of all the instances that have the same y value as the x instance. It creates all possible combinations of those values and replaces them in the selected features, repeating the other values in the other features as well as the label. Because of the nature of the features in some datasets such as DS1, it could not be done up to 4 features as it was in the original paper. After selecting 3 features, it would generate more than 100 million samples, and this process would not be only repeated by 2 more times, but it would also become more computationally expensive once another feature is manipulated. The intuition behind the instance selection for the sample seed is that, depending on the selected samples, we could have a very close reconstruction of the population by the adversarial sampling technique, easily distinguishable set of samples or hardly distinguishable set of samples. And for the sample seed selection, we had random selection for one experiment and used the support vectors for another. We kept the number of samples removed standardized at 200 samples. This is because Shirazi et al. Implied that 200 samples and 4 features would be enough to generate sufficient instances to make most trained models useless. Now I'm going to present a few definitions of SVM that, in case anyone wants to replicate this work or expand on it. So support vectors are going to be represented as alpha, the objective function as a big W of alpha, y is the label, and x is an instance. The weight vector is a function, is a sum of label, support vector, and each instance multiplied. The training criteria is the label, the previous weight vector multiplied by the current instance plus the previous bias, which has to be less than a threshold value. Instances are clustered into 3 arbitrary groups and it is thought of the existing possibilities. That is the regular fraud or the training phishing websites, the malicious fraud or the true phishing websites, and the regular non-fraud, which are the biggest part of the internet. Probability phi of m given z is the same of probability of m given z. The consistent belief of label and cluster given instance is as this formula. Scores are arbitrary numbers that are used as weights in the function of lowercase psi of x. Lowercase psi of x uses the consistent belief from regular and malicious samples and its respective scores to try to decide if a sample was well trained or not. The function uppercase psi normalizes lowercase psi. Now we have a new training criteria, which is the label times the predicted label times uppercase psi of x, which is less than threshold value, which is arbitrary. The update parameter u decides if the scores are going to be updated or not. The difference of errors, delta error, is just the previous error minus the current error. We did the score updates by the use of a hyperbolic tangent. To update the utility of a sample, we subtracted each sample's respective utility by itself, scaled by the hyperbolic tangent of the delta error. The intuition is that it will increase the utility of the sample as the error goes down. In a similar way, we updated the costs but adding instead of subtracting. The overview of the adversarial aware online SVM algorithm is for each sample, we're going to see if the training criteria is valid or not. If it's not valid, we'll go for another sample. If it is valid, then we add to a window of 100 samples, and this is a sliding window. We only consider 100 samples at a time. We do the training of an SVM with prior knowledge with a linear kernel, and if we are updating the scores, then we update the scores using delta error. If it is not updating the scores, then we're gonna see if it has reached the end of the period or not. If it has not reached the end of the period, we just do the training. If it has reached the end of the period, we're gonna update the parameters, which are the predicted label and the uppercase psi of x, and then we go for another sample. We're gonna measure our performance of the machine learning model with F1 score, which is the impact of false labels, the true positive rates or recall or sensitivity, and the accuracy or percentage of true labels and correctness. We're measuring bias using two metrics, which are class imbalance or label proportions and percentage of false positives, or number of samples that are classified as regular. We have three assumptions for the experiments, which are the process of creating the datasets was unbiased. The adversarial sampling technique mimics a real malicious agent, and the metrics are enough to measure the effects of selection bias. Experiments 1 and 2 aimed at creating a baseline for online SVM and adversary-aware online SVM on a moving window. In this graph, we can see the result of the performance of the adversary-aware online SVM against the online SVM. The continuous lines is the online SVM performance, and the dashed lines is the adversary-aware online SVM performance. The graph shows us that the online SVM was incapable of training with the S1, the S4, and the S5 because of the TPR values. It also indicates that datasets that have many features that are numerical will be problematic for SVM. On the S2 and the S3, the F1 score and TPR combined shows us that it was doing almost as good as a guess. For those reasons, even though the adversary-aware online SVM was very sensitive to which instances were removed, it outperformed the online SVM in all datasets. Experiment 3 was done with just one run and on holdout instead of five-fold cross-validation. In experiment 3, we evaluate the AA or SVM under an AST attack. Each time the AST used a random combination of features up to 2 features to expand the reserved 200 samples manifold. This table shows us that changing the scores had a great impact on the AA or SVM. All metrics dropped significantly on all datasets. In addition, it was even more critical on DS5, with TPR and F1 near zero, which means that it predicted almost every instance as being legitimate. To analyze the changes in the scores, we picked DS4 and DS5. DS4 for being a balanced dataset on both class labels and feature types, and DS5 for being the biggest and the most imbalanced of them all. Because of the disparity of the number of samples needed for a score to reach zero, the scores were analyzed based on the first 200 manipulated instances. The costs on DS4 and DS5 went to zero with less than 120 samples. As shown on graph, the utility of regular samples on DS4 went to zero with less than 160 samples, which means that for DS4 the scoring had no effect on the training criteria after only around 1% of the samples. Both the utilities on DS5 and the utility of malicious samples on DS4 have stabilized at some number other than zero, which was the desired behavior. It was already foreseen that once a score reaches zero, it has no way of coming back, i.e., it will stay at zero until the classifier is reset. We thought that using hyperbolic tangent as the update function, the scores will go up and down and either settle at zero or around some value, as the error fluctuates and gradually goes to a minimum. However, we did not foresee the number of samples that were needed for each score to reach zero, nor that it would happen with the error still high. Now we will see the result of the bias metrics and use them to answer the research questions. The first research question was confirmed as shown in this table. If support vectors are used as AST seed samples, then this percentage of false positives can go up to at least 10% in absolute number, or 25% relative to the randomly selected samples, and up to 20% in absolute number, or 100% in relative to the randomly selected samples. The second research question was dismissed, as there is no correlation between the class imbalance and the percentage of false positives as shown in this table. In all datasets that had false positives, with the exception of DS3, the class imbalance was almost constant, with the standard variation less than 1%. The class imbalance in DS3 varied more because of its size. Although the class imbalance had some variations, it did not change with the selected samples type, but with the dataset. The FP percentage varied according to the dataset and selected samples type. To answer the last research question, we need the previous two tables. On one hand, small perturbations on some features can bypass the AA or SVM and bring down the accuracy. On the other hand, even in the worst case, where the AA or SVM had a terrible performance during training and was facing generated samples designed to fool the classifier, the average percentage of false positives did not go over 50%. When it comes to online classifiers, adversarial attacks have an even bigger impact, as they can bias the classifier towards one class or the other. When the AA or SVM is changing scores during training, its performance decreases, but the decrease in performance in training is not linearly correlated with its bias metrics values. We say this because while clearly the choice of the seed matters, the change in false positives occurs in a similar way, but with different proportions, except for DS3. To summarize, we have shown that selection bias has an impact on the AA or SVM, while class imbalance does not have an impact on the AA or SVM. Now, more experiments are needed to determine if that impact is extended to other classifiers and initial parameters. If support vectors are used as AST seed samples, it will cause more misclassification. There is a class imbalance in the generated data by AST, but it does not affect the classification algorithm. When the AA or SVM is changing scores during training, its performance decreases, but the decrease in performance in training is not correlated linearly with its bias metric values. Thank you very much for your attention.